Welcome to this explainer. Today we're taking a literal microscopic journey into the hidden scientific battles that keep colors permanently locked onto a canvas. You know, whenever we look at a masterpiece in a museum, we usually get completely lost in the imagery, the emotion, or the history. But underneath all of that, there's this fascinating world of physics and chemistry at play. We're going to explore the exact mechanism of painting adhesion, how art literally meets chemistry.
Okay, let's dive into this. How does paint actually stick to the canvas? I mean, how does colored powder attach to a surface so firmly that it lasts for centuries? It's the fundamental mystery of how paint actually works. Think about it. If you just take colored dust and throw it on a wall, the first breeze is going to blow it right off. So how do we make it permanent?
To figure this out, here's our roadmap for today. First, we'll look at why color stays. Second, the science of adhesion. Third, we'll explore why paintings deteriorate. Fourth, the eternal brilliance of alfresco. And finally, the art of petrifying colors.
Section 1. Why does color stay? At its core, all paint is really just colored powder, which chemists call pigment. Now, these pigments can be crushed rocks, minerals, or even artificial dyes. But, as we just established, pigment alone needs a partner. It absolutely needs a binder, basically a type of glue, to stay put on a surface.
Now, what's really interesting about this slide is seeing how different mediums use entirely different physical and chemical rules to trap these pigments. Take oil paint, for example. It uses linseed oil as a binder and adheres through chemical oxidation. Acrylic uses a plastic polymer emulsion that actually fuses together. Watercolor relies on surface adsorption with Arabic gum, while traditional Sumi-E ink uses animal glue to create capillary action. And then there's fresco, which magically uses no binder at all. It relies on pure crystallization.
Moving on to Section 2, the science of adhesion. Let's zoom all the way down to the molecular level to see how these binders actually do their job in practice, especially the ones that rely on water.
So to keep pigment particles from this clumping together and sinking to the bottom of your paint tube, we rely on some absolute magic called protective colloids. These are natural polymers. Think Arabic gum harvested from plant sap or animal glue made of collagen. What they do is literally surround the tiny pigment particles with a hydrophilic or water-loving barrier. This microscopic shield keeps the colors perfectly suspended and dispersed in the water, totally ready for the artist's brush. But how do they actually stick when they dry? Well, even water-based mediums vary wildly. Watercolor uses Arabic gum, which gently glues the pigment right onto the very surface of the paper fibers. It uses delicate molecular forces and hydrogen bonds. It's a really elegant surface phenomenon. But Sumi-E ink, it uses animal glue, and that gets sucked deep down inside the paper's fiber matrix through capillary action, creating a deep, physical trap as the collagen solidifies. And here's the crazy part, these binders don't just hold the paint, they completely dictate the physics of light, changing how our eyes perceive the colors based on the refractive index. Oil has a high refractive index of 1.5, bouncing light off the surface to create that classic wet, deep gloss. Watercolor has a lower index, letting light pass right through the thin layer of pigment and reflect off the white paper behind it. And fresco, light penetrates right into the thick crystalline structure, bouncing around inside the stone for this gorgeous internal matte glow.
Section 3. Why do paintings deteriorate? Beauty is incredibly fragile, unfortunately. So let's shift the narrative to the tragic enemies of art. Why do so many masterpieces inevitably fade, crack, peel, and just lose their brilliance over time?
So the crucial point is that the answer comes down to organic matter. The vast majority of binders, like linseed oils, tree gums, animal glues, and acrylic plastics, are organic. This means they're built on a carbon skeleton, characterized by long, complex molecular chains. Now, these chains are incredibly flexible, which gives artists massive freedom, but they have a fatal, inescapable chemical flaw. Those long organic carbon chains are highly vulnerable to three major villains. First, ultraviolet light. It acts like a high-energy microscopic blade, slowly severing those fragile carbon-carbon bonds. Once broken, oxygen in the air swoops in, attacking the molecular wounds and triggering a runaway auto-oxidation cycle. Add heat into the mix, which makes the molecules vibrate so fast they literally tear themselves apart, and your organic binder eventually turns to dust. It's the ultimate villainous trio destroying our cultural heritage. Which brings us to Section 4, the eternal brilliance, alfresco. What if there was a way to completely defeat this decay?
Enter our protagonist in the battle against time, the ancient, completely inorganic technique of a fresco, or fresco painting. As we've seen, organic binders, like oil and acrylic, are doomed to eventually degrade, yellow, and crack because of those delicate carbon chains. But the fresco technique? It uses an entirely inorganic binder. It contains absolutely zero carbon chains. Because it lacks these vulnerable links, it's essentially immune to UV light and oxygen. Why? Because the painting itself literally turns into solid stone.
And this brilliantly illustrates the miraculous calcium cycle that makes this geological permanence possible. Step 1, you burn natural limestone at 1,000 degrees Celsius to create quicklime. Step 2, you add water to make slaked lime plaster. And Step 3, the absolute magic moment, carbonation. As the wet plaster dries on the wall, it absorbs carbon dioxide from the air and chemically reverts back into solid marble, permanently trapping the pigment inside its crystal matrix. The painting actually becomes a geological fossil.
But there is a massive chemical trade-off to this immortality. Wet fresco plaster is severely alkaline. If you put standard, delicate organic pigments into this mix, they're destroyed on contact. They just turn brown or gray. So artists are forced to use incredibly tough, inorganic mineral pigments, things like earth tones, cobalts, and iron oxides. And because they're raw minerals, they generate their color through unique atomic electron configurations, specifically a phenomenon called d-orbital splitting, giving them a profound, earthy brilliance that you just cannot replicate with artificial dyes.
Section 5. The Art of Petrifying Colors. Now, we're going to bring all this ancient chemistry together in the hands of the modern Japanese master, Koji Kinutani. To really understand Kunutani's work, you first need to understand the concept of giornata. It's an Italian term meaning one day's work. Because the plaster is actively absorbing carbon dioxide and turning back into stone, the artist has a strict, ticking clock window of just 8 to 12 hours to paint. Once it crystallizes, you cannot add a single drop of more color. It's an intense, do-or-die race against a chemical reaction with absolutely zero room for errors.
Now, Koji Kinutani took this rigid, high-stress technique and boldly modernized it. He invented what's known as tableau fresco. Traditionally, frescoes are stuck on immovable church walls, but Kinutani freed them, applying the plaster onto transportable panels. More than that, he modernized the whole process by adding explosive, deeply sculpted 3D textures to this ancient chemistry. He successfully combined the permanence of ancient stone with the dynamic, colorful chaos of modern art.
To summarize this process, I absolutely love this quote. The overwhelming power of his work comes from the physical combination of a do-or-die battle with wet plaster and the chemical reaction of colors petrifying into eternal brilliance. That perfectly captures the essence of what's happening on his canvas. His vibrant, almost chaotic energy is violently, yet beautifully, colliding with the strict, unforgiving laws of geological chemistry.
Let's move to and see how this builds. When you compare an oil painting directly to one of Kinutani's frescoes, the visual difference is night and day. Oil gives you a glossy, surface reflection, a slick, wet deepness because of the organic binder. But Kinutani's fossilized colors are entirely matte. They rely on internal crystalline reflection. The light goes into the stone and bounces back out, making the artwork look like it's powerfully glowing from within, possessing this profound material presence.
Which brings us to our final thought. The next time you stand before a masterpiece in a gallery, ask yourself, are you just seeing color, or are you seeing a microscopic battle of chemistry? Are you seeing fragile carbon chains fighting against the light and oxygen? Or are you seeing time, perfectly and permanently trapped in stone? Thanks for joining me on this explainer. I hope you never look at a painting the exact same way again.